All right, welcome to the University of Arizona Origins Seminar. Before I introduce the speaker, just a quick reminder, keep yourself muted during the talk and hold your questions till the end. If you have a quick clarification question, you can put it in the chat and then one of the organizers will ask the speaker. Yeah, and I think that's it. So today's speaker is Dr. Marina Kounkel. Marina got her bachelor's from the University of Toledo in Ohio and then did her PhD at the University of Michigan with Lee Hartman, where she was my office mate. She is now at Western Washington University, and before the talk told me that she will be moving to Vanderbilt next year. So Marina is an expert on the proper motions and dynamics of stars within our galaxy, which is what she's going to be talking to us about today. So Marina, the floor is yours.
Great. Thank you so much for having me here today. When you think about a star cluster, what is the first thing that comes to mind? Do you perhaps think of a globular cluster, which is an ancient reddish blob that is a remnant of the earliest wave of star formation in the galaxy? Do you perhaps think of an open cluster, which is full of massive blue stars that are waiting to die off? Or perhaps you're thinking of a young embedded cluster, which sometimes people classify them together with open clusters, sometimes not. But they're also full of stars, full of gas that is waiting to produce yet more stars, full of nebulosity and dust lanes. They're quite spectacular looking things. It is often said that most stars, including our own sun, has probably formed in a massive cluster such as the Orion Nebula. Now, that said, Orion Nebula is a rather special place in the solar neighborhood. It is, quoting dozens, if not hundreds of papers, almost verbatim, the closest region of the ongoing massive clustered star formation. But it is far from being the only young cluster. There are several others in Perseus, Serpens, Vela, or even a few others in Orion as well. Now, it is also often said that these young clusters tend to have very high infant mortality, that most of them would not make it to the age of 10 million years, and only a small fraction of them will make it to the age of 100 million years, something on the order of 5%. Now, when it comes to the Orion Nebula, maybe it will make it to the age of Pleiades, maybe it won't. I have heard various debates about it going either way. Personally, I think it probably will. But by that logic, if we expect only 5% of all young clusters to make it to the age of 100 million years, we shouldn't expect anything else to survive that long. And it all sounds terribly tragic, particularly if you have emotional attachment to these clusters. But at the root of this way of thinking is that we tend to view clusters as something that is compact, something that is isolated, something that exists outside of everything else. And what I'd like to show you here today is that there is a bit more to it than that. First, let's take a look at Orion in a bit more detail. Orion Nebula is located right over here at the head of the Orion A molecular cloud. Together, Orion A and its sister cloud, Orion B, represent the current epoch of star formation in the region. The stars in these clouds have an age of around 2 million years, but they are far from being the only young stars in this region. The belt stars, they're just a bit older. They have an age of around 5 million years, and they are part of this Orion OB1b population. This region, particularly centered at the star 25 Ori, is part of the Orion OB1a population, and they're also fairly young. They have an age of only around 8 million years. We have known about the existence of young stars in these regions for quite a long time, ever since the idea of the OB associations have been defined all the way back in 1960s. But despite that, the stellar content of Orion OB1b and especially Orion OB1a has not been nearly as well as characterized as the stellar content of the Orion Nebula. And there are several reasons for that. First, after a star loses its protoplanetary disk, it becomes very difficult to identify from any other field stars. They all look very similar just based on their photometry. And also there are a few ways that we can use to reliably confirm use of certain stars, such as through spectroscopy, for example. Getting spectroscopy of stars en masse is quite expensive, particularly compared to photometry. And it is much easier to cover a small area on the sky, such as a small compact cluster, with just a few telescope pointings, in compared to the large extended area, such as this. So until recently, all we can do is stare at these long exposure images and try to figure out how exactly does everything in Orion connect to one another, or if it's even all connected at all. Now, 2 years, something has changed that has revolutionized our view of galactic astronomy, something that has allowed to shed the two-dimensional confines and peer into that third hidden dimension. I'm talking, of course, about the release of Gaia DR2. And it is quite amazing just how much has changed since the release of Gaia DR2, when we actually know all the distances towards all the stars. Because in doing something as trivial as just drawing boxes in the sky and in the proper motion in the parallax space, we can quite easily identify all members of various clusters, such as the case with Pleiades, for example. And it never ceases to amaze me just how narrow the HR diagram for Pleiades is. Furthermore, if you're interested in the pre-main sequence stars, well, they're all located above the main sequence, so it's possible to select them just in this photometric space, but more on this in a bit later. But the true power of Gaia is revealed through clustering. How clustering works is, first you want to measure distance between all stars in your catalog. And it doesn't necessarily have to be a true two-dimensional or three-dimensional distance. You can throw in as many parameters as you would like. Then you would want to find the shortest distance, then the second shortest, then the third shortest, and so on and so forth, until you are able to construct a minimum spanning tree, kind of like the image here on the left. And what we want to do next is find an appropriate place to cut all the branches so that you end up with populations that are neither too large nor too small. So for example, here we would have 3 or 4 different populations, depending on how exactly you would cut all the branches. Now, none of these three points are trivial. There are dozens of different ways of how exactly you can measure distance, what you exactly define by a distance. And of course, how you define the shortest distance is a whole bunch of can of worms. And there are many, many different algorithms that all kind of do similar things in a slightly different ways. But it is worth keeping in mind that even though we do have all of these many different algorithms, in principle, even if they might have slightly different outputs with slightly different groups, with slightly different sources in each group, they should still trace the same underlying density distribution of the galaxy. And furthermore, it is also worth keeping in mind that even though the technique itself is called clustering, what you get out of it in the end are not necessarily physically meaningful clusters of stars, because the word cluster is a rather loaded term. Therefore, throughout this talk, I will try to avoid using the term cluster as much as possible, and rather defer to a more neutral term, group or population or anything along those lines, unless I'm referring to the classically defined open clusters. So with that in mind, we have applied this hierarchical clustering technique on Orion to reveal a wealth of different populations that have a very, very morphologically complex structure. Since I visited 2 years ago, I have talked extensively on this topic then, so I will try not to repeat myself too much. But one thing that has kept me up since then is the topic of supernovae. And supernova in Orion is a particularly fascinating topic because there has been one known to have erupted in this region at the top called Lambda Ori a couple of million years ago, right at the center, somewhere over here. And you can still see the remnant as the H alpha emission in this couple of degree bubble. And looking at all the stars in this region, they all appear to be moving radially away from the center of the cluster. And the further away these stars are, the faster they appear to be moving. And what likely has happened is when the supernova has erupted, it has cleared away the gas from the cluster and triggered the next generation of stars that continued on the same ballistic trajectory. Now, this is not the only H alpha shell that we have in the region. We also have a rather famous Barnard's loop that appears to be much, much larger. And eyeballing where the center of the Barnard's loop is, it's kind of roughly over here where the position of the star is. And if we were to look at the distribution of all the stars in the rest of Orion, you can see that they are all also appear to be moving away from the center of the Barnard's loop. Indeed, if we were to look at it three-dimensionally, we have this population that is moving towards us, and we have this population that is moving away from us. And they are all kind of forming a shell around the central point. And both in the radial velocity and in the plane of the sky, everything would have been collocated approximately 6 million years ago. Indeed, even the Orion Nebula, it's moving away from the central point into the filament. So it's possible to imagine that originally Orion was all one long filament from the bottom of Orion A all the way up to Lambda Ori. And that a supernova happened approximately 6 million years ago. It has cleared the gas, it has split the cloud, but as the shockwave has traveled into the filament, it has swept along the gas and allowed the formation of a singularly most massive cluster in the solar neighborhood. So probably Orion Nebula has formed as a result of a supernova. And I can talk about Orion for quite a long time. But if there's one thing I would like you all to take away from this, is that despite being so complicated and probably singularly most messiest region in the solar neighborhood, despite all of its messy star-forming history, it's actually quite dynamically cold. The velocity dispersion is less than 4 kilometers per second, less than that even if you take only a small part of it. And it is quite massive. The census of Orion contains over 10,000 stars. Now, most of them are located in the Orion Nebula, but there's still plenty of other stars distributed throughout. So how long will it take for all of these stars to fully dissolve into the galaxy? How long will it take for them to lose any memory of the velocity with which they have formed? How long will it take for us to look at this region of space and no longer see this massive population that has once formed there? Would it be another 10 million years, 20, 50, 100? And as much as I like Orion, it's not entirely a unique star-forming region. There are plenty of other massive filamentary looking populations, such as Sco-Cen, such as Vela, and Taurus comparatively is quite low mass, but it has even lower velocity dispersion. So how long will it take for these populations to fully disperse? And by that logic, if we are taking a look at 20, 50, 100 million year old open clusters, should we expect them to be isolated? Or should we expect them to have an extended halo of stars around them that have formed together with them in these filamentary clouds as a comoving group? The idea of comoving group is not entirely new. We have known of approximately a dozen of them within a volume of space of around 100 parsecs in radius. Very few of them have been known beyond that, but for a fairly good reason. In order to find a comoving group, you need to have information on accurate velocities of stars available across the entire sky. And until recently, the best source of velocities that we had came from the Hierarchical survey, which really didn't necessarily have good sensitivity or resolution to give us precision in position and velocity of the stars beyond 100 parsecs. But now that we do have Gaia, perhaps we can do a little bit better and extend that boundary just a little bit further. So with this in mind, my clustering algorithm of choice was HDB scan. And the reason why it was chosen is because it's particularly suited for identifying both very dense clusters as well as very diffuse low mass populations simultaneously. Most other clustering algorithms would struggle with that. And the clustering was done in 5-dimensional space, position in the sky, parallax, and proper motions. To avoid various distortions, both in distance and position of the sky, the velocities were converted to physical units, to kilometers per second. And to achieve uniform sensitivity in distance, the clustering was done in various slices, which in distance that were painstakingly stitched together. The result of this analysis is this. In blue are approximately 1 million stars that have been clustered together into more than 8,000 populations within 30 degrees of the galactic plane, within approximately 3 kiloparsecs. And in contrast, in yellow are many of the previously known open clusters in the same volume of space. And as you can see, the difference in terms of spatial coverage is quite different. And the good idea about finding all of these comoving groups and populations is that presumably they have all formed at the same time. Therefore, it's possible to determine their ages through isochrone fitting. And for the most part, they do follow quite nice isochrones. You can see how the youngest populations in red have a sizable pre-main sequence that drops down to the main sequence, and then the older populations in green or blue, how their high mass stars are evolving away from the main sequence. And this is just one projection in which we can show the HR diagram using the Gaia bands. You can switch to something different. For example, with Y's bands as a color, and Y's being mid-infrared can really show as the reddened sources due to the presence of protoplanetary disks. And you can see that these disks, they deplete rapidly as the populations age, but they still persist up to quite sizable ages, up to several tens of millions of years. And if we were to look at the total disk fraction as a function of age, you can see that they continue this exponential decay, even to quite advanced ages. So if you're interested in protoplanetary disks and would like to study how they are evolving in more distant populations, this would be an excellent sample to look into. Together, this catalog of approximately 1 million stars is probably currently the largest catalog of stars with known ages. So we can take all of these populations that we have identified and color code them by age. Again, with red being the youngest at the age of approximately 1 million years, to purple being the oldest at the age of several giga years. And this is just how they look in the plane of the sky. We can look at them in various different projections. First, again, galactic the longitude versus galactic latitude versus parallax versus various velocity components. And this looks fairly busy. So let's just, for the time being, look at the youngest stars with the ages of less than 30 million years.
So Marina, before you go on, Caitlin had a question on the previous slide on disk fractions, asking if those disks are all protoplanetary disks, or if there are also debris disks or if they're debris disks at 50 million years.
Well, they could. This was a very rough selection of just sources that fall into this parameter space. So I expect it could be a mix of either.
All right, thank you.
So let's take a look at just the sources with ages of less than 30 million years. And what becomes particularly prominent looking at the middle panel in particular is that different populations have different peculiar velocities relative to one another, obviously. But an individual population can remain coherent for several dozens degrees in the plane of the sky in these long string-like forms. And it's not just a projection in one particular dimension. If we were to look at all dimensions, these populations remain string-like in all of them. And several dozen degrees correlates to a few hundred parsecs in physical units at these distances. And the coherence remains even in the radial velocity space. Now, the clustering wasn't done in radial velocities because they are not quite as precise as proper motions, nor are there quite as many of them with Gaia. But the fact that we do see the same smooth coherence shows that these structures are indeed real and not just a random selection effect. All right, so this is what's happening at the youngest age ranges. What if we were to look at something that is a bit older, let's say on the order of 1 billion years? Well, it is much messier, but with careful poking at the data, it is possible to identify these strings of stars even at these age ranges that still remain coherent in all of the different dimensions. And to clarify, various strings can contain a cluster at their center, and some of them do, some of them do not. But separating the sample explicitly into these long strings and these more compact groups that do not necessarily have an extended halo of stars around them, and separating how the stars look like at different ages, we can find that strings are ubiquitous at the youngest ages, and the strings tend to be fairly sharply defined in the velocity space, with only a handful of stars belonging to a more compact, more isolated groups. On the other hand, at the older age ranges, most stars that are still clusterable at these ages tend to be more compact, more isolated, whereas there are only a handful of fairly diffuse strings. Looking at it in a different way, we see once again that strings are ubiquitous at the youngest ages, but they tend to go away after approximately 100 million years. On the other hand, more compact groups don't necessarily even come into prominence until the ages of several hundred millions of years. Furthermore, if we were to look at the number of stars in a population as a function of age, at the youngest ages, it's possible to have anywhere from a few dozens of stars to several thousands of stars. So there's a very wide range of masses and densities. On the other hand, at the oldest ages, it is fairly rare to have more than a few dozen stars, no matter if it's a string or a more compact group. And it's likely that the populations that are still identifiable at these old ages have started as some of the most massive groups that are still forming right now. So there appears to be this envelope that encompasses the number of stars that are still recoverable as a function of age. So with this in mind, what is the origin of this extended structure? Well, it's unlikely to be caused entirely by tidal stretching, because we would expect things to start compact and then stretch out, not quite the other way around. And many of these strings, once again, don't even necessarily have a compact cluster inside them. Some of them do have a cluster, but it may not necessarily be at the center. It may be at either end or anywhere else. Rather, it's likely that the structure is primordial, that we know that stars from giant molecular clouds are filamentary. And whenever you're going to have enough gas, you're going to start forming stars. So it stands to reason that the filamentary cloud morphology is going to be preserved in the stars that they will form. And these strings are slowly dissolving over time. They are losing stars into the galaxy. After a while, only the densest part, most cluster-like part, will remain. But some of the more massive ones will be able to survive for a little while longer. And if we were to take a look at where the strings are in the three-dimensional view, not just in how they look in the plane of the sky, here we're just looking at the strings that are younger than 50 million years, and they have been traced along their spine. The sun is located at the center of this image. The galactic center is to the right. This is the Sagittarius arm. This is the Perseus arm. This is the local arm, and along the local arm, there have been recently identified a giant gas structure that people refer to as a Radcliffe wave that is probably very, very strongly related to the actual trace of the local arm. And as you can see, when we look at these very, very, very young strings, they tend to be oriented in parallel to one another, perpendicular to whatever spiral arm they are located closest to. And this trend is going to be even particularly stronger if we were to look at the longer strings in preference to the shorter one. And this orientation does seem to be significant because it may have implications of how they might have formed. Indeed, if we were to look at the extragalactic observations of molecular gas, people have observed these various feathers that are gaseous structures that are protruding away perpendicularly from the spiral arms. And chances are when you have gas, you're going to have stars. So it stands to reason that these stellar strings likely have formed from these feathers. And this likely had an effect of, on how the giant meteor clouds are forming in our own galaxy as well. Now, I will point out that the correlation of the strength being perpendicular to the spiral arms really only valid for the younger age ranges, because at the older age ranges, there is a lot of very fascinating evolution in the structures that we are recovering. Unfortunately, I don't necessarily have time to go into that in detail, but this may show us how exactly our galaxy has been evolving with time. But another thing that is important to keep in mind is that even at the youngest ages, if you want to have a full census of stars that have formed at a given epoch, you would not necessarily be able to recover all the stars in a population through hierarchical clustering. As populations age, they are dissolving into the galaxy, and even in populations as young as 1 million years, some stars are very eager to leave their nests, and some do it more violently than others. There have been several dozens of young runaways identified that have been ejected from their parental clusters that are moving with speeds of several dozens, if not several hundreds of kilometers per second. And they have been ejected through gravitational interactions with some of the other stars in the population that they inhabit. Most of these runaways have been identified associated with the Orion Nebula, and there are several good reasons for that. First of all, once again, because Orion Nebula is so massive, chances are there's going to be more runaways associated with it than with most other more diffuse populations. Second reason is people have studied Orion Nebula for a very long time. Therefore, we have very pristine membership lists for this cluster. And third of all, because the cluster is so young, the young stars stand out much more easily relative to the field stars. And that is a very important thing because these young runaways correspond to only a fraction of a percent of the total sample of stars that have formed in the cluster. Therefore, you need to be very, very sure in their age to confirm that they are runaways and not just chance alignment field stars, because otherwise you're going to get overwhelmed with contamination. Youth of stars in population such as Orion makes it fairly easily standing out. For example, if you know where exactly the population is, what exactly the distance to it, and it has an age of only a few million years, then it becomes fairly straightforward to identify all the pre-main sequence stars and separate them from the main sequence stars or the red giant branch stars. You might have a bit more confusion when you're dealing with the more higher mass stars, but for the most part, as long as you restrict yourself to the lower mass ones, they are fairly straightforward to separate. But what if you wanted to do it across the entire sky? Then it becomes a bit trickier because you are averaging different populations together. You are and as the populations age, they get closer and closer to the main sequence, so that the contrast between the main sequence and the pre-main sequence stars washes out. And you have the binary sequence somewhere over here, which is going to act as a source of contamination. And the farther and farther you look, the greater and greater the effect of the extinction is. So many of these massive stars get scattered into the pre-main sequence parameter space. So it becomes rather non-trivial to identify which stars are indeed pre-main sequence and which stars are more involved. Thankfully, as I've mentioned, we do have currently probably the largest catalog of stars with known ages, and therefore we cleanly can separate which stars are pre-main sequence in this catalog and which stars are main sequence. And the good thing about big data is that you can show it all at a computer, and it will be able to learn from that data to identify various patterns and features, and it will be able to produce yet more data in the future from what it has learned. I don't quite have time to describe how deep learning works specifically, but it is a fascinating topic that is beneficial to practically every field in astronomy, and it allows us to really data mine very large data sets, quite straightforward. So we were able to train a classifier that identifies pre-main sequence stars and separates them from the more evolved counterparts. So the stars that this classifier identifies with higher confidence have darker colors. The stars that it identifies with lower confidence are with paler colors. And this looks fairly smooth, but the highest confidence sources are plotted on top. And the classification is really done on the source-by-source basis using various color bands as well as distance and extinction towards stars. Furthermore, not just classification, we can determine the ages of stars without relying on theoretical isochrones, which may have issues because they don't quite match the data in all the ways that we want them to match. So we have the youngest stars at the top, we have the oldest stars at the bottom. At the highest confidence levels, the identified sources very clearly carve out a space for themselves away from both the main sequence and the binary sequence, as well as from the red giant branch stars. At the lower confidence levels, we are a bit more sensitive towards the older ages, as old as 40 to 80 millions of years. And we are also slightly more sensitive towards the more distant sources. But of course, there is a bit more contamination from unrelated stars. And so with this, we can actually take a look at how the structure of the solar neighborhood is evolving as a function of age. Right now, we're looking at the stars that have ages less than 2 million years. We have a lot of usual suspects if you have studied star formation in the past. We have Rho Ophiuchus, we have Orion A and B, Serpens, Taurus, Perseus. Many of these regions probably are quite familiar because they are corresponding to the bulk of what we have known of the star forming history of the solar neighborhood for a very long time. And as a reminder to various people, many of these regions are forming what is commonly referred to as a Gould's belt, that these star forming regions appear to be on the high galactic latitudes with respect to the galactic plane. And there have been many debates over a course of many decades as to what might have caused the formation of the Gould's belt. But now let's take a look at something that is a bit older, from 2 to 5 million years. And we are still recovering populations that still may be a bit familiar: Upper Sco, the rest of Orion, something that's a bit more distant, Cygnus OB2 or NGC 2264. This is how everything looks at 5 to 10 million years, starting to get a bit over Sco, San, and Vela, 10 to 16 million years, 16 to 25 million years. Note how between, as we look at the older and older ages, the things become a bit more diffuse. And finally, ages older than 25 million years. And this looks pretty much like in an uncharted territory. There haven't really been many studies of these regions in the past at all. So once again, let's take a look at everything in a three-dimensional frame, with the sun once again being at the center. There is a bit of a lack of young stars within the volume of space of approximately 100 parsecs in radius. And that has been known for quite a while, that there are really very few young populations in that volume of space, with the exception of TW Hydra, for example, which is fairly low mass. And the reason for that is that we are located within a local bubble. There's a cavity cavity in the interstellar medium that doesn't necessarily have much molecular gas and can be traced through various methods, both through extinction and through X-ray emission. But what's interesting is that at the edge of the local bubble, we do recover a ring of stars, and the typical age of these stars is around 40 million years. There are a few younger stars here as well, such as those in Sco-Sen, such as those in Taurus, but the bulk of the star formation in this ring really occurred approximately 40 million years ago. And I don't necessarily have plots for that, but this ring really fits quite well with the dimensions of the local bubble that people have reported in the past. Furthermore, there have been some discussions about, well, why exactly is Taurus and Sco-Sen are equidistant from us, but they are located on the opposite parts of the sky, and they do appear to have radial velocities that are traveling in the opposite direction, radially away from each other, radially away from us. Well, if the local bubble has formed as a result of a supernova, it probably has cleared away the gas, and it has probably could have formed this ring. But what I do find rather fascinating is that if you're to look away from the ring, there does appear to be something of a gap at the distances between 200 to 300 parsecs. Not exactly unexpected. There have been very few young star-forming regions known in that volume of space. But this gap isn't filled up by the older stars either. And then once we get to the distances of approximately 300 to 400 parsecs, we do get younger populations such as Orion, Perseus, Serpents, as well as several other older ones. So as weird as it is for the sun to be at the center of a local bubble, it would have been even more weird if it was at the center of two different bubbles. So it is probably quite likely that the same event that have formed this ring at approximately 100 parsecs have also formed the outer ring as well. Perhaps there have been two different shock waves from the same event. And it probably also gives an answer of how exactly the Gould's belt have formed. Because if all of these different populations are associated with the Gould's belt, such as Orion, Taurus, Perseus, and Sco-Sen, and we are tracing the outline of the local bubble, it's probably the same event that have formed both of them. To summarize, currently we have the catalog of stars with known ages, and this catalog is very useful, going to be very useful for a number of different investigations of how actually stellar properties and populations properties and galactic properties are evolving with time. And we can see that young stars are commonly found in extended strings and not necessarily just forming in clusters. And some of these populations can remain coherent for quite a long time, and we are able to find them if we just look for them. Thank you.
All right, thank you so much, Marina. If you have a question for the speaker, you can raise your hand using the raise hand feature under the participants tab. So I don't see any questions yet, so I'll take organizer's prerogative. So it's astounding the amount of information you can pull from this data set, but I'm kind of wondering what's next. Like, what are the outstanding questions that Gaia can't solve, and are there any like future observatories that can like let us go even further?
The future thing that I'm personally excited about is that as we are working with this specific data set, I have alluded to it in the past in terms of runaways, but I want to do a more detailed census of identifying young runaways across different ages and trace it back where exactly they're coming from to figure out how the stars are interacting. In terms of the things that Gaia can't do, an observatory that I am currently feeling quite passionate about is TESS, because we can identify the ages of the pre-main sequence stars or the ages of populations in bulk, but through TESS, through Gaia chronology, or with Rosita through X-ray emission, we are able to look at the activity as a tracer for age. And so far there is quite a lot of evidence that we would be able to calibrate our chronology much better than the current calibration. And then we will be able to apply it to even more stars. So I expect we might be able to produce the catalog of as large as 5 or 10 million years. for stars that we actually can measure ages. So that is going to be quite exciting in the future.
Yeah. All right. Question from Everett.
Excellent talk. I was laughing at your jokes, but I was on mute, so thank you for the great talk. I was wondering if you have a hypothesis for why you noted these linear structures were perpendicular to the spiral arms. I wonder if you have a speculation or hypothesis about why.
Yes. So let's go back to. I imagine part of it might be due to some feedback from young stars, in that there isn't necessarily as much gas that is found in the other areas, so it just kind of compresses the gas along the spiral arm, or it might be just through dynamical effects of how the gas in the galaxy is evolving. We are working with a few modelers that are trying to compare their models to the observations. So hopefully we'll have a much better constraint on that in a couple of years.
Thank you.
Can I ask a follow-up question? Because I don't have raised hand button. So exactly the same question is, do you think the magnetic field is playing a role here?
Could be. There have been some observations also in external galaxies that, oh, no, that has been in our galaxy, that when, I don't quite remember the orientation, but the magnetic fields are oriented one way relative to the spiral arm, but when you look at the dense gas, the orientation kind of flips. So it could be that the, well, it's a bit of also a chicken of the egg. Are the magnetic field existing outside of the gas, or is the gas driving the magnetic fields? It probably is a bit of both. That once you start forming various asymmetries in the gas, they're going to start accreting more and more gas in this specific direction. But I'm not an expert on magnetic fields, so I'm not sure how well I can answer to more than that.
Yeah, I asked that question because there were cases where the filaments and when the polarization map was made, they tend to have more or less kind of, some of the string filaments have a perpendicular polarization. So
yes.
Yeah.
So I think the magnetic fields are perpendicular to the spiral arms, but they're also perpendicular to the filaments, and you can kind of observe this transition that at the lower densities they're oriented one way, at the larger densities they're oriented the other way.
Thank you.
All right. Are there any final questions for Marina?
Actually, I have one more question. Sorry. So DR3 is coming out. How much do you think the Gaia DR3 is going to help?
I think the overall conclusions are going to still be roughly the same, but Gaia DR3 is going to have better precision in parallax and proper motions. Therefore, we would be able to be a bit more confident in our identifications of more distant structures. Mm-hmm. Just as a confirmation that they are indeed as coherent as they appear to be, and are not going to change with better resolution. I think Gaia DR3 might also have a bit better sensitivity. Right now, the parallaxes are not very precise for anything that is fainter than G of 18. Mm-hmm. I'm hopeful, I don't have the exact numbers, but I'm hopeful that at least the colors and the precision might be able to work a bit better at the fainter stars. So we might be able to increase the census that way. And finally, not the EDR3, but the proper DR3 are going to have binaries and radial velocities. And that would also make it very, very exciting to look up at various statistics.
Thank you.
All right. At this point, I would like to invite everyone to unmute and thank Marina for a wonderful talk.
Thank you.
All right. Thank you, everyone. See you back here next week.
Mm-hmm. Bye.
Bye.